Hello, everybody. We're going to continue our conversation about the sun. And despite what it seems like, the sun is constantly changing. The sun is a very active object. We don't really experience this day to day. The sun seems pretty much a constant in our lives with little fluctuation. However, in the details, which is what we're going to look at, the sun is quite active. So, in this and then the next video, we are going to look at solar activity. We will start our look at solar activity through an investigation of the sunspots to understand the grand cycle of solar activity and to understand that it's linked to the magnetic field of the sun. So I'm going to have this uh, image in the presentation, but since we're going to be talking about sunspots, I just want to go ahead and show you what sunspots look like, give you a little bit of an orientation to them, and compare them to the size of the Earth. So sunspots, as you can see here, are not perfect in shape. They're not perfectly round. There are these blemishes on the spots. These are not black pits into the sun. What you're really actually seeing is just cooler material on the photosphere. Since it's cooler, it's not emitting as much light. Thank you, Stefan Boltzmann. In fact, it's emitting so much less light that it appears black compared to how bright the surroundings are. We also have a deep part of the sunspot, the darkest part of the sunspot, what we'd call the umbra. Should bring back some memories. And then you have the surrounding, which is a little bit redder and dimmer in color, what we call the penumbra. And they can appear in chains or they can appear in paired spots, but there always is a connection. You're never going to find a single isolated sunspot. They appear in chains or spots. And yes, this sunspot is about the size of the entire Earth. All right. So this and the next video are all about the active sun. And the sun is not a regular, it's not really that much more active or less active. Actually, it's kind of less active than a lot of stars out there. But this is what stars do. Stars have a complex activity to them. Whenever I say activity, I'm talking about events that happen on short timescale events that can be highly energetic. In this image over here, we're looking in the ultraviolet. So you can see it has all of this craziness going on the surface. If you look at the sun in the ultraviolet, it looks like a very incredibly different place than invisible light, where you can see these prominences, these arcs of superheated material. Right here, you're seeing a solar flare. This is hugely energetic eruption from the sun. This one was a very, very large flare, a X8.2 class flare, one of the strongest ones that we've seen in modern history. And yes, this explosion on the surface of the sun, and you can think of it as an explosion on the surface of the sun, not a chemical explosion, more of a magnetic explosion, but it's releasing energy equivalent to tens of millions of nuclear bombs all exploding at once. And it can eject the material out into the solar system, which, if that material hits the Earth, can have profound effects like wiping out our entire power grid and throwing us back to zero power for up to 18 months. We would like to know if we're going to get hit by something like that. That's what we call a Carrington level event. And yes, it would stop modern life as we know it and cause trillions of damage up front and leave cities like New York, Mumbai, the largest cities in the world, pretty much everywhere in the world, without power for somewhere between 6 to 18 months. Talk about a natural disaster of natural disasters. So we care about studying the active sun since it could have a profoundly huge impact on our modern life. Okay, in this video, we're only going to talk about the sunspots in the solar cycle. The next video will hit the more exciting bits, the prominences, the filaments, the solar flares, and the coronal mass ejections, and a little bit about how they can interact with Earth. A key thing to get whenever we're talking about the activity of the sun, it can all be related to the magnetic field of the sun. What's going on with the magnetic field of the sun, which is an intensely strong magnetic field that is constantly changing. So we can link all the solar activity to the magnetic activity of the sun. All right, let's look at a high resolution image of a sunspot. Now you can see it's not completely dark in the center right here in the umbra. There's actually, it's just a much dimmer. It's giving off less light. So let's just go through the basics of what sunspots are. They are quite large. The typical sunspot is about 10,000 kilometers across. That's the size of the Earth. And they appear as darker regions on the photosphere of the sun. And why do they appear as dark regions? They are simply cooler. And it's because these are going to be related to magnetic fields, and the magnetic field lines that are coming through here are suppressing the convection just beneath the photosphere, allowing that material to cool down because it's not getting replenished with warm material via convection. More detail than you probably wanted to know, but I think is super cool. And so within the umbra itself, we're dealing with a temperature that's about 4,000 Kelvin. Ridiculously hot. If you could remove that material and put that out in outer space and look at material that's 4,000 Kelvin in outer space, a black body of 4,000 Kelvin, that's going to be really, really bright. It's going to be giving off lots of electromagnetic radiation and lots of visible light. So why does it appear dark here? Well, let's compare the brightness, the luminosity of this dark spot with a temperature of about 4,000 to the typical photosphere, which you can see the granulated surface over here with a temperature of 5,800 Kelvin. I can just do a quick comparison of how bright these two things are relative to one another by using good old Stefan Boltzmann, everybody's favorite. So the luminosity, the brightness of the spot compared to the photosphere, it's just going to be the ratio of their temperatures, 4,000 divided by 5,800. Raise that to the fourth power since the energy or the brightness is related to temperature to the fourth power, and it's 20% as bright. So it's a fifth as bright, which makes it appear darker because it's cooler. And if we were to look at the magnetic field within this region, which we will shortly, we'd notice that the magnetic field within a sunspot can be up to 100 times stronger than the surrounding photosphere. So sunspots are created by some aspect of the magnetic field of the sun. They can form over days, and once they're there, they can last for weeks to months before they dissipate. And how many sunspots we see on the sun, if you were to go out and use a solar telescope to look at the photosphere of the sun and start counting sunspots, you'd notice over an 11-year cycle, what we call the solar sunspot cycle, or just the solar cycle, that you would go from not seeing very many sunspots like we are right now to seeing a whole bunch of sunspots, and then back to not really seeing any sunspots. And to go from almost no sunspots to a whole bunch of sunspots to no sunspots again is roughly an 11-year cycle. It varies. It could be 10 years, it could be 13 years, but on average, it's 11 years. And since these are located on the photosphere, they will rotate with the sun, which is something that Galileo noticed with his observations. And you can see right here that here are sunspots on the sun, and you can see the sunspots rotating with the sun. And this is how you could actually determine the rotational period of the sun, which is a little bit more complicated, as we'll see soon. But I just want to show you some sunspots of what they look like. You can see the dark umbra, you can see the penumbra, you can see some chains, you can see a pair. This is the same image that I've shown you already. And why are they dark? They're darker because they're cooler. All right, so the sunspots are really related to magnetic field lines. And the magnetic field of the sun ends up getting really, really tangled, like a tangled ball of yarn. You could imagine just one little thread of yarn. It pops up out of the sun and then makes an arc and goes back down into the ball of yarn. Picture that in your head, except now instead of yarn, picture magnetic field lines, and you basically have your model of a sunspot. So sunspots are caused by where magnetic field lines of the sun pop up out of the surface and then arc and go back down into the surface. If we actually wanted to look at an edge on view, where down here would be the solar interior, a convective zone. Here would be our photosphere, the very thin thing. And here we're actually seeing an image of the chromosphere. You can see this arc of material that's mapping out these magnetic field lines as they pop up out of the South Pole and go into the North Pole. So this is why we always see sunspots in pairs, because they're going to have a north part and a south part. What we call the polarity is the north-south orientation. And since we're dealing with magnetic fields, for every north part of a magnetic field, there's a south part of a magnetic field. There's no such thing as a magnetic monopole. And really, you can almost just picture a bar magnet almost underneath the sun. And where you have the part of the magnetic field lines popping up out, you'd have a sunspot, and where it goes back in, you'd have a sunspot, because that's going to prevent the convection from bringing up new, fresh, hot material within that region, so it'll cool down. And what's kind of cool, details that I don't go into, is that in one cycle, you'll have a certain polarity where you can look in the polarity how the north-south are oriented. So in this part. Let's imagine one cycle where this one would be the north and this one would be the south part of the magnetic field. And then the next solar cycle, so 11 years later, then you'd flip the polarity. And then 11 years after that, you'd flip the polarity, which gives you a longer 22-year cycle of the sun to go from basically a north-south polarity to a south-north polarity back to a north-south polarity. Almost as if the magnetic field of the sun is flipping north-south, north-south, north-south every 11 years. And I just can't get over showing you really, really cool pictures of the surface of the sun. So here we're looking at X-ray and visible light, combining that together with some UV light as well. I forgot to put that on the slide. And we can actually see the magnetic flux tubes of magnetic, well, we have magnetic field lines that are coming up out of the sun and going back in. And those magnetic field lines will constrain, will keep in charged particles, ions, super hot atoms that have lost their electrons. And those ions will travel along within the magnetic field lines almost as if they're trapped in these tubes. And they'll get super hot and they'll glow, giving us what we call flux tubes, which you can see right here. You can see they come up out of one sunspot, shown by where the red is, and go into other sunspots. And it's not so clean as the image I showed right here. It's quite messy, but that's how you get your sunspots. It's where the magnetic field lines are popping out of the photosphere and going back into the photosphere. And we can really link this to the magnetic field. If you remember when we talked about light, we had this weird thing called the Zeeman effect, that in the presence of a magnetic field, some electron energy levels will split into multiple energy levels. And how far they split is determined by how strong the magnetic field is. So we could take a spectrum along, say, this line right here through the sun that has some photosphere and then goes into the sunspot and then the deepest part of the sunspot. And we could look at one of the spectral lines, one of the ones that would experience the Zeeman effect. And as we go down, it's narrow, it's kind of broad as it starts getting into the sunspot. And then as it hits the thickest part of the sunspot, boom, you can see it fully split into 3 different spectral lines. And how wide it's splitting, or how wide it looks like it's here, the spacing between each of these split lines, or how wide it is right there, gives us a measure of the magnetic field strength. So we can actually determine how strong the magnetic field is on the sun in general, and really with these sunspots, we can see that it's much more intense where the sunspots are. Okay, so I wanted to show, I've mentioned several times now that we have this sunspot cycle. Let's give some terminology to it. And let's go ahead and take a look at the right side first. This is where we currently are. We're in a solar minimum. We're at the start of a new cycle right now and in solar minimum. So if you go outside, normally we'd invite you up to the roof to look through our solar telescopes. It's not super exciting right now because there are very rarely sunspots. And on this top image, we're viewing this in white light so we can see the photosphere. And in the bottom image, we're viewing in the UV so we can see the chromosphere. Actually, is this UV? No, I think that's H alpha. So here you can see the solar minimum, no sunspots. Chromosphere, not a whole lot going on with it. You wait about 5.5, 6-ish years though, and you'll go from minimum to the maximum, and look at all those sunspots. Now you see a whole bunch of sunspots on the sun. And the chromosphere is really, really active. And notice where you see the sunspots, you also see the plages. These these whiter areas, these hotter areas in the chromosphere, due to the magnetic field interactions going on. So you'll go from a minimum to a maximum, back to a minimum again, and that on average takes 11 years. But it's what we call quasi-periodic. Periodic would be 11 years. It's always 11 years. You could set your clock by this cycle takes 11 years. Quasi-periodic means on average it's 11 years, but one cycle it might be 9 years, the next cycle is 10 years, the next cycle it's 11 years, the next cycle is 9 years again, and then it's 13 years. But on average, over all the cycles, it's an 11-year cycle. And of course, being creative namers, whenever we see a lot of sunspots and a lot of activity, we would say that the sunspots are at maximum and the activity is at maximum. We call that solar maximum. And whenever there's no sunspots, the number of sunspots is at their minimum and activity is at its minimum, we call that solar minimum. We're very creative namers here. And I just want to go ahead and show you. So here's the historical trend, and we'll take a look at that again. Of the y-axis is number of sunspots, the x-axis is time. So you can see that it goes up, reaches a maximum, minimum, maximum, minimum, maximum, minimum. And this is going back about 200 years, a little over 200 years. So you can see all of these cycles. This is as long as we've been tracking sunspot cycles. And the average time from maximum to maximum or minimum to minimum is 11 years. And here we're going to zoom in on the most recent. We just ended cycle 24. And we are starting cycle 25, where this red line is the predicted number of sunspots as a function of time. Notice that these are predicted to be pretty weak solar cycles compared to some previous ones, which have been really, really high maxima. So I just want to show you that yes, we're constantly tracking this and let you know where we are, where we're in cycle number. We're just starting cycle 25. The last time I taught this class, I was talking about how we're at the end of cycle 24. And how can we actually track the sunspot numbers? How can we actually start building a bit more knowledge about what's going on with the sunspot cycle? So here, this bottom plot is just showing basically how much of the sun's surface are covered with sunspots as a function of time. Essentially the exact same data that we're looking at here. So you can see the cycles 12, 13, 14, all the way we are in 25 right now. But another way we can do that is we can count the number of sunspots. And then we can put a dot like, oh, we see a sunspot. Let's mark what latitude on the sun it's at. So is it at the equator? Is it a little north of the equator? Is it a little south of the equator? And we can do that as a function of time. So we can go ahead and let's just pick 1950 right here. So 1950, at 1 of the month, we would go, oh, we see a sunspot and it's at 30 degrees south, put a dot. We see another one at 30 degrees north, put a dot. So this is just mapping out how many sunspots there are as a function of their latitude. And you get this really cool pattern where at the start of you have a solar minimum where there's almost no sunspots. And then at the start of a cycle, you have few sunspots that appear at high latitudes. And then as you get more and more sunspots, as you go towards maximum, the sunspots move closer to the equator. And then at the end of a sunspot cycle, you see very few sunspots very close to the equator. And then you repeat over and over and over again. These almost look like you have pinned a butterfly onto this plot. So we call this the butterfly diagram. It's a way to get extra information where we can track the number of sunspots as a function of latitude, which gives us additional information because the sunspots aren't always appearing at the same location. It's telling us something about what is controlling this sunspot cycle. And to understand that, we have to introduce, I have to introduce something that seems a little bit odd, but is as natural as anything that rotates that's not a solid body. So if I take a solid body, like this ball, and I rotate it, everything's rotating at the same speed, right? Everything completes its 360-degree, same angular speed, I should say. Every part does this 360 degrees of rotation in the same amount of time. If this was a ball of water that I could just have freely floating and I could spin it, the entire thing wouldn't rotate at the same speed. It would experience what we call differential rotation, where the material at the equator would rotate around faster than the material at the poles. It's just how a non-solid body rotates in space. What this really means for the sun is the rotational period at the equator is about 26 days. And as you move northward or southward, as you go to higher latitudes, the rotation period increases. So that by the time you reach the poles, near the poles of the sun, that material takes 34 days to make one complete lap around. So the material is moving around a lot faster at the equator than it is at the poles. Kind of weird, but this is going to have an effect on the sun's magnetic field that's going to give us our sunspot cycle. Because let's start at a solar minimum, where the magnetic field of the sun would be very, very controlled, look very much like a bar magnet. where you could draw some of the magnetic field lines, say going through like so. And then as the sun rotates over time, the equator is rotating faster than the poles. And that rotation is dragging along the parts of the sun that are generating the magnetic field. So they drag the magnetic field along with it. So then after a little bit of time, you have magnetic field lines that are started getting stretched, pulled around the poles. You do that even longer. It's like winding it up, and you're stretching them, winding them around more and more. Eventually it gets so wound up and tangled that parts of it will pop up, where you'll get these arcs that pop up off of the surface of the sun, coming out of and back into the sun. These are our flux tubes. These are our magnetic field lines that are coming out of the surface of the sun and back into the surface of the sun, where we see sunspots. So it's the fact that the sun has differential rotation, that it tangles up the magnetic field, and eventually the magnetic field will sort of reset itself, it'll sort itself out and go back to a nice controlled solar minimum thing. The odd part is when the way that it sorts itself out is it gets so tangled up that in this case, we're looking at, this would be the south magnetic pole. This would be the north magnetic pole as it's drawn, because the lines go out of the south and into the north. Whenever it resets itself, the magnetic polarity would flip. So what was the magnetic south pole will become the magnetic north pole, and what was the magnetic north pole will become the magnetic south pole. So after 11 years, the polarity, the entire polarity of the Earth's or the sun's magnetic field flops. And since it resets itself every 11 years, we have the 11-year sunspot cycle. That's what I have for you about sunspots. Next time, we'll talk about the exciting, very short, high energetic events and potential things and effects they can have here for us on Earth. I'll see you in that video.